everyone, welcome back to iTTV. Today we're looking at Form 5 Chemistry, Chapter 1, Lesson 3 on Rate of Reaction. The title for today's lesson would be Factors that Influence the Rate of Reaction. So what are examples of factors that influence the rate of reaction? There are in total 5 different factors that will affect any reaction. Firstly, would be total surface area of a solid. Secondly, concentration. Thirdly, pressure. This is only for gaseous reactants. Fourthly, temperature. And fifthly, catalyst. So those were the 5 different factors that will influence the rate of reactions. Now, what are the effects of these factors on the rate of reaction? If we look at total surface area of reactants, the bigger the surface area, the higher the rate of reaction. Second factor, concentration of reactants. The higher the concentration of a reactant, for example hydrochloric acid, the higher the rate of reaction. Third factor, pressure of gaseous reactants. The higher the pressure, the higher the rate of reaction. Fourth factor that influences the rate of reaction will be the temperature of the reactants. The higher the temperature, the higher the rate of reaction. And last factor will be the presence of a catalyst. Now, catalysts increase the rate of reaction. More specifically, positive catalysts increase the rate of reaction. So these are the effects of the 5 factors on the rate of any reaction. Let's move on to show how these factors affect the rate of reaction. We start off with a simple experiment. The aim of this experiment is to investigate the surface area of a reactant. And the problem statement would be, what is the effect of surface area on the rate of reaction? And therefore, with the problem statement identified, we can postulate a hypothesis. Our hypothesis for today's experiment would be, the bigger the surface area of a reactant, the higher the rate of reaction. That is our hypothesis for this experiment. And when we are planning any experiment, we have to think about the variables. We have to look at the manipulated variables and the responding variables. So let's look at the slide. For this experiment, the manipulated variable will be the surface area of the reactant, while the responding variable will be the rate of the reaction. What are the control variables? They are the concentration and the volume of the acid, because in this experiment we are using an acid called hydrochloric acid. Control variables are basically factors that are held constant throughout a few experiments that are repeated. And in this case here, the concentration and the volume of the acid used would be the same when we repeat the same experiment a few times. The setup of the procedure is as shown in the slide, and the apparatus and materials are listed also in the slide. So the chemicals that are reacting will be calcium carbonate, reacting with hydrochloric acid to give us calcium chloride, water, and carbon dioxide gas. So let's look at the procedure. Firstly, we fill a measuring cylinder with water, invert over a basin of water, and clamp it to the retort stand. Next, we adjust the water level in the measuring cylinder and record the initial reading. Measure 25 cm cube of 2 mole per dm cube hydrochloric acid and pour it into a conical flask. Weigh 3 grams of eggshells. Add hydrochloric acid into the conical flask containing the eggshells. Fix the delivery tube as shown in the diagram and start the stopwatch. 6th step, record the volume of gas at 30-second intervals. Swirl the conical flask slowly throughout the experiment. Repeat steps 1 to 7 using 3 grams of fine calcium carbonate powder. Using the same axis, plot the graph of volume of carbon dioxide against time for both the experiments. And when we are starting the experiment, we'll be keying in the data into the table as shown in the slide. So for coarse calcium carbonate represented by eggshells, we will tabulate the data in the table as you can see in the slide, and we will record down the cylinder readings at every 30-second intervals. So let us demonstrate this experiment using eggshells to represent coarse calcium carbonate. Eggshells have very low surface area. Therefore, we predict that the rate of reaction would be slow as well. So over here, I have my 25 ml hydrochloric acid that I will pour into the conical flask that contains the eggshells. And I will slowly read out the readings as the gas is produced at 30-second intervals. So let us start now. And I stopper it. And I start the timing for this. Okay, so at 0 seconds, there was 0 moles of CO2 produced. Now, let us try and see for the first 30 seconds interval, what is the reading on the measuring cylinder that will represent the volume of carbon dioxide that is released as a result of the reaction of calcium carbonate with hydrochloric acid. The first 30 seconds would be about 20 mils. 20 mils. As you can see, the rate of reaction is lower because the amount of reactants is decreasing with time. Okay, we're going to our next 30 seconds interval. For the next 30 seconds interval, we register about 28 mils. 28 mils of gas. Let's wait for the next 30 seconds interval. Well, the amount of gas produced is getting really slow. Okay, coming up, the next 30 seconds would be about 32 mils, and thereby we wait for the next 30 seconds interval, coming up very fast. We register about 35 mils. 35 mils. So gas is still being produced, as you can see, because the amount of reactants have not been exhausted. That means there's still some remaining reactants. Now the next 30 seconds is coming up. Next 30 seconds, we register about 39 mils. I repeat, 39 mils of carbon dioxide gas released. Slowly and surely, bubbles are being released. Okay, we're going to our next 30 seconds interval. For the next 30th second interval, we register about 42 mils. 42 mils on the measuring cylinder. And we're going almost to our second last 30-second interval reading. As you can see, the rate of reaction is getting to be very low. Okay, 5, 4, 3, 2, 1. This will be 44 mils. 44 mils. And we're reaching almost our last 30-second interval. We're measuring how much carbon dioxide produced in 4 minutes. So this is the 4th minute. Okay, it's going to be the end for this part of the experiment. Okay. We register about 45 meals, and that's the end. 45 meals of CO2 released in 4 minutes when we use coarse calcium carbonate. Okay, that was the experiment using eggshells, which represent coarse calcium carbonate with a very small surface area. Let us repeat the entire experiment, specifically repeat steps 1 to 7 using fine calcium carbonate. Fine calcium carbonate has bigger surface area, therefore we predict that the bigger the surface area, the higher the rate of reaction. So over here, I have my 25 ml hydrochloric acid, and I will be pouring the acid into the conical flask. Okay, so let me get ready with this. Okay. And I will start the stopwatch. So it's very fast with 30 seconds. At 0 seconds, there was 0 meals here. Now, at 30 seconds, I would say that there would be 78 meals of CO2, 78 meals. So for the first 30 seconds, the first reading is 78 meals over here. This means 78 meals of carbon dioxide produced. Let's wait for the second 30-second interval. You can see the rate of reaction is going slower. And the next one is about 86 meals. 86 meals. 86 meals. For the second 30-second interval is 86 meals. Now, for the next 30-second interval will be about 93 meals. 93 meals. As you can see, the rate of reaction is so low as time goes by. And the next 30-second interval will be at 100 meals. So the rate of reaction, as you can see, is so high using fine calcium carbonate. So that's our last reading. It didn't even reach 4th minute, and it already accumulated 100 meals of carbon dioxide. So we finished both experiment A and B. Experiment A uses coarse calcium carbonate, and experiment B uses fine calcium carbonate. Let's look at the board as in how the graphs for A and B would look like. So let's draw the graph of the volume of carbon dioxide collected versus time. So the y-axis would represent the volume of carbon dioxide collected in cm cubed versus time in minutes. So the graph for experiment A would look like this. This is for A. Now, the graph for B would have a higher rate of reaction, something like this. It would eventually reach having the same volume of carbon dioxide. B would be on top. Now, as you can see that the graph B has a steeper initial slope. This means that B has a higher rate of reaction, and B used fine calcium carbonate. Fine calcium carbonate has a bigger surface area, thereby higher rate of reaction. Whereas for experiment A, it used coarse calcium carbonate, which has a smaller surface area, thereby the rate of reaction was slower. So with that, this shows that the bigger the surface area, the higher the rate of reaction, as shown in experiment B and experiment A. Now, if we look back at the slides, we can conclude that in 4 minutes, the maximum volume of carbon dioxide gas collected for experiments A and B should be the same. Reason being, the same concentration and volume of HCl and mass of calcium carbonate were used. What is the conclusion that we can state about this experiment, whereby we had tested the effect of surface area on the rate of reaction? The conclusion would be, the smaller the size of the solid reactant, the bigger the total surface area exposed for reaction, and therefore the higher the rate of reaction. Now, for the next part of the experiment, we will study the effect of concentration on the reactant. Our aim of this experiment is to investigate the effect of concentration on the rate of reaction. The problem statement being, what is the effect of concentration on rate of reaction? So, with the problem statement identified, we postulate that the hypothesis would be, the higher the concentration of the reactant, the higher the rate of reaction. What are the variables? The manipulated variable will be the concentration of reactant, while the responding variable would be the rate of reaction. The control variables will be the volume and concentration of HCl and temperature of solutions, because this experiment uses HCl. The apparatus and materials needed for this next part of the experiment is listed as in the slide. And we are looking at sodium thiosulfate's reaction with hydrochloric acid, as you can see in the chemical equation in the slide. It will give us 4 products. One will be sodium chloride, sulfur, sulfur dioxide, as well as water. So we will test the effects of different concentrations of sodium thiosulfate with hydrochloric acid. Now let me just run through the procedure. Firstly, measure 50 cm cube of 0.2 mole per decimeter cube of sodium thiosulfate solution using a measuring cylinder and pour it into the conical flask. Next, place the conical flask on a filter paper marked with X. Measure 5 cm cube of hydrochloric acid with a measuring cylinder. Pour the hydrochloric acid into the conical flask, swirl the flask, and start the stopwatch immediately. Stop the stopwatch and note down the time when the X is no more visible. Next up, we repeat steps 1 to 5 using different volumes of sodium thiosulfate solution that has been diluted with distilled water to make up to 50 cm cube. Lastly, we plot the graph of A, concentration of sodium thiosulfate against time, and B, concentration of sodium thiosulfate against 1 over time. So let us start the experiment now with the first conical flask, which contains undiluted sodium thiosulfate solution. So I will pour in hydrochloric acid, 5 milliliters, into the conical flask. Right now here, I'll put it on top of the filter paper with the cross. And as I pour it in, I will start my stopwatch. Okay, so here goes. So I start to swirl, 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 and I think the X is slowly disappearing from view. And stop. It takes about 13 seconds for the X to disappear. So I will key it in 13 seconds for the first experiment. So let's start with experiment 2, we have a diluted sodium thiosulfate concentration here, and I'll place it on the cross. So here I have 5 ml of hydrochloric acid again, and I will slowly add it into the conical flask. Okay, with that, and I'll start to swirl. Okay, swirl. The X is starting to disappear, as you can see. Slowly, slowly, but surely. Needs a little bit more time. And there. For second experiment, it needs 0.22 seconds. So I'll key that into the data. Okay, let's start with the third experiment. The third experiment contains an even more diluted concentration of sodium thiosulfate. So I'll put it on the cross, and I'll add another 5 ml of hydrochloric acid. So I'll reset the stopwatch, and now here goes. And I start the stopwatch, and I start to swirl. Swirl. This should take an even longer time because this is an even more diluted solution of sodium thiosulfate. You can see that the X is slowly disappearing. Okay, for this one, it takes about 27 seconds. With our last experiment 4, let me place it on the X. And same thing, I'll put in 5 ml of hydrochloric acid. And I start the stopwatch. And I swirl the conical flask. This would take an even longer time for the cross to disappear from view because it's the most diluted concentration of sodium thiosulfate. But you can see that the X is slowly disappearing from view. Slowly and surely. This one takes an even longer time. This one takes 40 seconds. A nice number. And that ends our experiment, and we'll do some more tabulations. Okay, I will then calculate the 1/, time from the time taken. For the first experiment, it takes 13 seconds. For the second experiment, it takes 22 seconds. For the third experiment, it takes 27 seconds. For the fourth experiment, it takes 40 seconds. And that was about the experiment on testing the effects of different concentration of reactants on the rate of reaction. We've gotten the experiment results tabulated in the table. So let's now draw 2 graphs to illustrate how different concentrations of sodium thiosulfate will affect the rate of reaction. So let's jump to the board to have a look. The first graph shows the concentration of sodium thiosulfate. The concentration will be in molar, which represents mole per decimeter cube, against time in seconds. As the concentration decreases with time, this can be illustrated on the graph. So this shows that the concentration of thiosulfate, the lower the concentration, the longer the time it takes to complete the reaction. Now for the second graph, we'll look at Again, concentration of sodium thiosulfate, again in molar, which represents mole per dm cube, versus time in seconds. Now this one would be a straight line originating from 0, like that. Take note, this is 1 over time, and 1 over time represents rate of reaction, and you will get a directly proportional graph. And this graph clearly illustrates that as the concentration of sodium thiosulfate increases, the time needed for the reaction to complete decreases. And that's the relationship of the graph. Well, that ends our lesson on Chapter 1, Lesson 3 of Form 5 Chemistry. We have looked at factors that influence the rate of reaction. Thank you so much for watching iTTV, and we look forward to see you again next time. See you!